Okay, let's start class. Last time we talked about the bias variance trade-off, which is a very fundamental principle in the statistical learning and machine learning. Okay? And we talk about this example. And here I'm listing, these slides talks about some math in the bias variance trade-off. Just show you the proof behind that. Okay, and we can consider the bias variance in two situations. One is estimating the parameters. The other one is the prediction on a new observations. So these are the two different situations, right? The first one is estimation problem. The second one is prediction problem. Estimation of a parameter is related to the statistical inference. Prediction is different, right? So in these two different situations, we can prove the bias variance trade-off applies in both situations. Okay, so I won't talk about the details. So here, these two proofs are very similar. So the key is all the cross product terms in the expectations are all equals to 0. Okay, and since this is an applied course, I will just list the proof here. If you are interested in that, just read it, and it's not difficult to understand. So you should be able to know why these can be decomposed into the bias variance. Okay. Now, this is another simulation which shows the bias variance trade-off also applies in the classification case. So here, the response is binary, either blue cross or red circle. And the true boundary is a sign function. Above the sign function, 80% of chance to get blue cross. Below the sign function, 80% of chance to get red circle. Okay, so that's the underlying true data generating mechanism. So based on this underlying true mechanism, we should predict all the points above the sign as blue cross. Below the sign function should be the red circle, right? But of course, there are some random errors, okay? So here we have training set, 100 observations, and we use the k-nearest neighbors. And this is the code to generate the data set. Okay? So here I ran the KNNs on a training examples. And the KNN, the K is the number of nearest neighbors that we used. Okay, so I range the K to a big range. So here I'm just showing the KNN results with K equals to 3, which is in the dark green, and 9, which in the red color, and blue is the 21. So the blue color is the smoothest, okay? And dark green color with K is 3 is the most complicated. Okay, and the smooth dashed line, the underlying true function, that's the true boundaries. Okay, so here I'm trying to examine the bias variance trade-off on 2 points. Okay, so this one is at negative 0.5 and positive 0.5, right? So this point, negative 0.5 and positive 0.5, right? So this is one point. Another point is here is 0 at the x1 and 0.1 at x2. So which one is easy to identify? Which one is easy to classify? Of course, this point is the point that is easy to predict the class status because it's far from the boundary, right? But this one is very close to the boundary. So this one is a difficult one, not an easy one, right? So I just want to show these two points to see the bias variance trade-off, okay? One is easy, one is difficult. So this one is the difficult one. So the top row shows the points, which is this one, the difficult. And the bottom row is the easy one, okay? So you can see for the top one, the true probability should be 0.8, right? You can see at the bottom, the tick mark at 0.8, that's the true probability. But the estimated probability is around 0.6. So what is the bias? Bias is about 0.15, okay? And the standard error is 0.08. And you may ask, how can I get the bias and the standard deviation? I can get that based on the simulation. I run the simulation. I randomly generate 50 data sets, 50. So each data set, I can estimate the probability. I can, for this point, and I can do that 50 times, so I can calculate the center. Then I can get the bias. And also, since I can have 50 replications, so I of course can get the standard deviation, right? So this is a simulation, so we can repeatedly generate the data from the population. Okay, so that's why we can get the bias because we know the truth. And also we can do that repeatedly, sampled from the population so that we can get the standard deviation. Okay, so when the K is 21, so this one is for the KNN at K is 21. So that means the model is simple. We have a large bias and small variance. Okay, so when we reduce the K, that means the model, the KNN boundary becomes more complicated. The model is more complicated. So you can see the bias reduced slightly, but the variance increases. And when the K is 3, that means the model has a very complicated boundaries. And the bias is 0 or no bias. So the bias is further reduced to 0. And the standard deviation somehow is really large, 0.25. 3 times bigger than the case with 21 for the standard deviation. In other words, the variance is 9 times larger than the one at K is 21. Okay, so you can see the bias variance trade-off, right? So that's why the fundamental picture, where is it? Yeah, that's the fundamental picture. So when the model complexity is low, that means when the K is high value in the KNN. When the K is 21, we have a high bias, but low variance. But when the model complexity is high, that means the KNN with K is small. When the K is 3, we have low bias, bias is 0, but the variance is high. Okay, so what is the optimal model? What is the optimal value for the K in the KNN? It should be somewhere between. Okay, so that's the fundamental picture. And this one still holds, right? So for the easy point, okay, you can see that for the easy point, the bias is 0, even with K is 21. Because what? Because this is the easy point. Even with a very simple model, we will get no bias. And when we reduce the K, means we increased model complexity. The bias actually kind of increased. Why? Because this is the easy point. We don't need too complicated models for that easy point, okay? So, but in general, the bias variance trade-off still holds. Not just for this point, for if we consider all the points, the bias variance always holds. So this one shows the misclassification rate over 50 data sets. For each data set, we apply the KNN at K from 1 through 21. Okay, so each curve represents a data set, a particular data set with different values of K at KNN. Okay, so the blue one is the average of the misclassification rate over these 50 replications. So you can see when the K is 9, achieves the average is the smallest. So that tells us probably the K is 9 is the optimal value for the K. Okay, and these are the code here, sample code here. Okay, so this concludes the supervised learning for the introduction. Okay, so let's start the unsupervised. I will just briefly introduce unsupervised learning. So for the unsupervised learning, as I said at the beginning, we only have X variables. We don't have a response variable called a supervisor. We don't have that supervisor. So we are not interested, most of the time we are not interested in prediction for the unsupervised learning because we don't have a response variable. So the goal in unsupervised learning is not prediction, but trying to find something which is not expected or unknown, something interesting from the data set. Okay, for example, is there an informative way to visualize the data? Can we, for some high dimensional data, can we find some clustering structures, like some meaningful subgroups in the data set? Right, so these are the questions which we are very interested in, and we would like to use the unsupervised learning to answer that question. So unsupervised learning in general is more challenging and tends to be more subjective because we don't have an objective supervisor here. And it's difficult for the investigator to evaluate the quality or the performance for the results. Okay, so often the unsupervised learning is part of exploratory data analysis. So here I listed some examples. Okay? You can take a look. Like the first example is a gene expression data set for among the breast cancer patients. We are trying to find some subgroups among the breast cancer patients. Like here, this is a gene clustering example. And the technique used here is the microarray. So the color scheme is used to show its gene expression levels. Okay, so for each row represents a patient that has a cancer. Okay, for each column represents a particular gene expression levels. If it's red means positive, green means negative, black means on the average. Okay, so we want to find out some subgrouping structures among the patients. And we want to find some subgrouping structures also among the variables, among the genes also. So this is an unsupervised learning case, right? And also you can see these are the two other examples. Okay, so unsupervised learning is also very popular. Like the second one is used in the online shopping. Okay, so to find out a particular subject's preferred items based on the subject's history of shopping history. And the third one is the search engine to trying to displaying the searching results according to other people's with similar searching patterns. So these are the unsupervised learning examples. And one of the methods that we will talk about in this course for the in the unsupervised learning part is market basket analysis, and which is a very popular and powerful association rule minings. So just trying, so this one is trying to find those frequent patterns or the associations probably leads to some causal relationships among the set of items in the transaction database. Like the, like the customer who bought the bread, what is the chance of for that customer also bought the egg or the toilet papers? Okay, so we want to find those frequent items that will appear in the same shopping cart. Okay, so this is the market basket analysis. And this one is the principal component analysis, which we will cover in the unsupervised learning part. So one of the applications for the principal component analysis in the image analysis is the eigenface. So let's say we have a database, image database, which can which includes about 1 million subjects. Okay, so you can represent each subject through an image. So we will have 1 million image, right? Or we can do it in a more efficient way. We instead of represent each image by itself, we can have some eigenface like here on the left side. So these are the bases for the image of faces. Then each individual image is a weighted sum of these eigenfaces. Like the first image is 20% of the eigenface 1 minus 30% of eigenface 2 plus 80% of eigenface 3 and so on. So it's a weighted sum of these eigenfaces. Then we will have an image which is very similar to the image one that we can. So that is a much better way to, an efficient way to represent the data. And also we can reduce the dimension from a high dimension in the raw data to a low dimension so that we can visualize. So principal component analysis not just can represent the data in a more efficient way, but also can help us to reduce the dimension and to visualize the high dimensional data in low dimensions so that we can see the interrelationships and probably some clustering patterns among those objects. Okay, so that is another application in the unsupervised learning. Okay, so the last slide shows some different terms from the computer science area and the statistics area, which talks about the same thing, but using different terms. Because statistical learning that we focused here overlap with AI's learnings. So in in artificial intelligence and computer science, they use different language. They use different technical terms. So here I listed a short table that just shows a few of them. Like here, when you see the network graphs from the computer science or the machine learnings, it corresponds to models in statistics. When we see the weights in computer science, in the artificial neural network, in statistics, we call it parameters. And estimated weights are the estimated coefficients, like that, okay? And learning in computer science, that means fitting in statistics. Generalizations means test set performance in statistics. Supervised learning in statistics, we call it regression or the classifications. Unsupervised learning, like in statistics, we have density estimations, clusterings, and so on. Okay. And one of the papers that I strongly recommend you to read is Statistical Learning, the Two Cultures by Leo Berman, who is one of the most well-known statisticians, which contributes a lot who is like one of the leading statisticians that introduced the machine learnings and artificial intelligence into the statistics field. Okay. Although this paper was published quite long ago, but still can give us lots of different perspectives to see the traditional, what's the difference between the traditional statistics and machine learning. And what, as a statistician, why we need to learn those algorithms that were developed from the computer science area. Okay, so read that paper. This paper is not technical at all, but very interesting. So it's very fun to read this paper. Okay, so read it. You can download it. Just search it online and you can easily find it. So in this paper, two of the main points that Leo Berman made is traditional statisticians rely too heavily on the modeling, on the data modeling. So that's one culture. That's one of the two cultures he mentioned, that he mentioned. And another culture is the algorithmic cultures from computer science, using those like an artificial neural network, the trees, deep learnings. So that is another culture. So this paper discusses the pros and cons from these two cultures and see what are the main difference. So that can give you a very good pictures of what is the difference between the traditional statistics and machine learning in a non-technical way. Okay. Any questions? Okay. If you don't have any questions, let's move to the model assessments and the selection. The handout is posted in the Moodle. And by the way, I've already posted the homework 3 in the Moodle. Okay, so you can start it to work on the homework 3. Homework 3 is due next Tuesday at 1:30. Okay. There were still I will post it the homework 2 solutions sometime this week. Okay. The reason that I didn't post it today is because still 2 students haven't submitted. Okay, so model assessment and selection. So first, we need to talk about the loss function. Okay, so for the regressions and the classifications, due to the different natures of the problems, we have different loss functions. Okay, for the regression, the most commonly used loss function is squared error. A less commonly used one is absolute error. For the classifications, we have 0-1 loss, and we have deviance, and we have some others. These, I just listed 2 for each problem, but there are several other choices. And you may ask why we need to have multiple loss criteria, loss functions for the same problem. And the reason is that different loss function actually have some slightly different properties, and evaluate the performance from some different perspectives. And each loss function has its own pros and cons. Like for the regression, compared with squared error loss, absolute error loss is better when we have some extremely outliers in the samples. That means if we have some sample which have very large errors, large means far from 0. It could be very extremely large in the right side or extremely small in the left side. Okay? So in that way, if we have that kind of situations, absolute loss is better than the squared loss. Why? Because absolute error is more robust to these outlying residuals. Why? Because it emphasizes less on those outlying residuals by just using their absolute values. But for the squared error loss, it used the squared error. Let's say most of the errors are within -1 and 1. We have one outlier which has the residual equals to 1,000. Okay, and if you squared it, that will be what? That will be 1 million. Right? So that is 1,000 times larger than the absolute loss. You see that? So that's why using different loss function, they have different properties. Then you may ask, so now why not just using absolute error instead? But the drawback for the absolute error is most of the case, absolute error does not give you a unique solution. So you don't have the uniqueness properties. It can have many solutions which gives you the same results. So that's no good. And also, when you do the optimizations, absolute error is they have a closed form. So it's much easier to optimize. And the solution is usually unique. So that's why from the computationally speaking, people likes to use squared error. And also theoretically speaking, we have much more theoretical results about those related to using the squared error compared to the absolute error. Okay, so that's why in practice people still likes to use squared error. Okay. Similarly, for the classification, we have the same similar situations. So the training error is the average loss over the training samples. Test error is the average loss over the test samples. And another error is called in-sample error. So what is in-sample error? For the in-sample error, first of all, it's expected. Okay, so this is very important. So this is a expected prediction error. On what? On the training set. Okay, so that means when let's say we have a data set, we have a training set, and we fitted a model, right? F hat on, so that, let's say, based on the training set, okay? We have this. So the y I is equal to the estimated plus the residuals. Is that right? But why we have expected here? The reason is that we can still fix at the xi. So the x value doesn't change in the training set. But now I regenerated the y. Given those x are fixed. So in other words, we have another set of data with the same x values as the training set x values, but the y is regenerated. When we regenerate those y's, these y's will be slightly different. Is that right? Remember the assumption? Y has two parts. One is the determinist part, two is the random part. So the x is the same, so the determinist part is the same. But the y is two parts. So determinist part doesn't change if x is still fixed. But the random part will change. The random error will be different. So that's why the new y will be different. So we have a prediction error on the training set, condition on the training set, right? So that is called in-sum. And that expected prediction performance with x is still the same, condition on the training set is called in-sum. Okay? And the next one is a more general case. It's called generalization error. This one doesn't condition on the same x as the training data. It can be any x as long as x is a possible value for the data set. Okay, so that also has a name called extra sample error. So that is the expected prediction error over an independent test. So which is what we most interested? Training error, test error, in-sample error, or generalization error? Which one? In practice, which one is the one that we are most interested in? We want to find a model to minimize what? Not for the training, that's obvious. What about test error? Many people will say, okay, we want to find a model to minimize test error. Is that right? No. Ultimately, we don't want to find a model that minimizes the test. Minimizing the test error, that's good, but that's not our ultimate goal. Our ultimate goal is what? Is to find a model which minimizes the generalization error. So that will minimize the expected prediction error over any independent test set, not just this independent test. Right? So in a more general ways. Okay, and you may ask, oh, that's not possible. A model minimize that. So here, so that's why the generalization error is what? Is the expected prediction error over an independent. Okay, not the prediction error over an independent. Is expected. Okay, so that's for the in-sample error, it's not, because that only focuses on the training set X. Right? So ultimately, we would like to find a model that minimizes the generalization. So that is the ultimate goal. Okay, but in practice, we usually cannot find this. So we need to find some proxy. So to approximate the generalization error. So that's why one approach is, instead of finding the model that that minimizing the generalization error, which is usually very difficult to get, we would like to find a model which minimizes the in-sample error. Okay, so that's a easier question to be answered. And also the test error can also use, so we want to find a model to minimize the test error on a particular test set. Okay, so as an alternative to minimize that. Okay, so the performance assessment is very important, and especially the generalization performance of a statistical model relates its prediction over an independent test set. Okay, and the reason the generalization performance, to evaluate that performance, is very critical is because it can help us to select the models, select the optimal models, and also it can help us to evaluate the model performance, right? And there are three types of model assessment. The first one is the in-sample error. So that's just what I said here. It's very difficult to evaluate the generalization error. Instead, we can use the in-sample error approach. Okay, so in-sample error is the performance on the samples used to develop models. But there are two subclasses. The first one is without any adjustment, just using the training error. That is no good because there's an in-sample optimism, which we will see that in the next slide. And with adjustment, that's okay. Like various of information criteria, like AIC, BICDs. So these are all the in-sample error approach. And the second approach is the internal approach, means we have a data set, we can split the samples into multiple parts and use like a cross-validations or validation approach or bootstrappings to internally evaluate the model performance. And that can be used to estimate the generalization performance, not just in-sample error, but generalization error. External approach, that means we have an independent test set to evaluate. And you may ask which one we should use, right? It seems to us like this one is the best because this one or these two may be the best because this one is not really estimating the generalization error, but in-sample error. But I tell you, this one is also very useful. Why? Because there are some cases that we have a small data set. Let's say if you have, let's say, 50 observations, a few variables. And it's very difficult to use internal approach or external approach because you already have just very limited amount of information. You cannot bear further splitting the data set into training and test. You don't have that many samples available. And getting these samples are very costly. Okay, so in that case, you should consider like in-sample approach because in-sample approach does not require any split of the data set. Internal approach is also very good for the small data sets. Okay, especially for those cross-validation like a leave one out cross-validation, which we'll talk about in a minute. Okay, but what about the external? External is very useful if we have a big data set, large amount of samples. In that case, we can have a part of the data can be used to evaluate the model performance as a test sample. Okay, because we have enough data set, enough samples to fit the model and evaluate. Okay, so that's why you have to, we cannot say which one is better. So we have to decide it the most appropriate one for a particular case. Okay, so that's the fundamental picture. We've already talked about this one twice, so let me just skip. So for the in-sample optimism, for the in-sample approach, let's say that T is the training set, okay? And the Y0 are the new response values at each of the training points. Okay, so here the Y0 is the one that I mentioned is the regenerated response values. But with the X value is the same as the training. So X doesn't change. But for the response value, we sampled again. So we have N new response values, but X doesn't change. Okay, so that's the notation. So the in-sample optimism is defined as this one. So this part is the training error. So we have a training set T, so we have a training error. Okay, and what is this part? This part is given the training set. So if we have a given the training set, we have a F hat, right? You give me a training set, I can fit a model, and that model is called F hat, right? And then L is the loss. Remember the loss function? So L is the loss. Loss function has two arguments, right? One is what we observed, and one is what we predicted. So that's the two arguments for the loss. One is the Y, that's what we observed. The second one is what we predicted. So we can have a loss. For the squared error loss is what? Is the Y minus Y hat, and take the square, is that right? And then of course take the summations. Okay, so that's the loss for the fitted model, between the fitted model and the regenerated Y values. And take the expectation over the YI zeros, because these Y zeros, these are regenerated. So the expected value for the loss, for that loss, okay? And the minus the training error. So that, and take the average. So that is the optimal optimism. So ideally, if the optimism is 0, that will be the ideal case. Why? If the optimism is 0, that means what? The training error is the same as what? What is this one? What is the first part? The first part, if you think about it, it is what? It is the expected value of the in-sample error. Is that right? So the first part is called what? Is called in-sample error. That's the expected prediction error conditioned on the training set. That's exactly the expected prediction error conditioned on the training set. Is that right? So that's the in-sample error minus the training error. And that gives the optimism called in-sample optimism. So in-sample optimism is equals to the in-sample error minus the training error. Okay? So if the in-sample optimism is 0, that's perfect. Then we can just use the training error to find out the model that minimizes the in-sample error. But actually, in reality, it's not. It's not equals to 0. It's actually, we can show that the optimism, first of all, this is also a random error. Okay, so you may ask, why this is also a random error? Because here in the training data, this is already take the expected value over the y0. Y0 are the new response. But it also is this is also a random variable. Why? Because this is a random variable because of the training set. In the training set, what is the random variable? The training set, we can write it as what? As the xi, comma, yi, and I from 1 through training set, let's say, has n observations. So what is the random part in the training set? The random part is a yi. So this is also random. So that's why this optimism is a function of what? Is a function of yi. It's taking the expected value not over yi, but over y0. Y0 is the new response value to evaluate its performance. But here I'm talking about the training data. In the training data, we have the yi. This also has randomness. If I keep the same x, but regenerated the y, and then use that to fit the model, that model will be different from this model. Is that right? So the f hat will be different if I regenerated the y values for the training set. Remember? Right? So we have a training set. So these yi's in the training set also can change. So that's why the OP is also a random variable. And D here, the expected value is not over y0, but over y. The y are the y's in the training set. Okay, so when you look at the expectation, you always need to be clear. What is the expectation over? It's over to the y0 or y's here. That's tricky, okay? So it's still a random variable, but when we take the expected value over y, we can show the expected value is that. If the loss function is a squared error loss, or if the loss function is a 0-1 loss, and some other loss function can also apply. So this is a quite general result. Okay, so it shows the expected value for the optimism is actually related to the covariance of yi and yi hat. Okay, now we have a covariance. So I hope you know what is the covariance. Okay, so the covariance is related to the correlation, right? In practice, how we calculate the correlation. So the correlation can be calculated equals to what? Equals to the covariance divided by what? Square root. Let's say covariance between the A and B, okay? And the correlation between A and B is equals to the covariance between A and B divided by what? Divided by the square root of variance of A times the variance of B. Okay, so that's the formula we calculate the correlation. And this formula also shows the relationship between the correlation and covariance. Okay, so in practice, if let's say we have an ideal model, what is an ideal model? So yi equals to, remember the general assumption, fxi plus epsilon. So in practice, let's say, suppose we have an ideal model, which means we have the F model, that's the true model, and the Y is generated in that. So what is the correlation between the yi and the yi hat? And by the way, what is yi hat here? Yi hat is what? If we have a model is fx, so the yi hat is what? Is f, fxi, is that right? If we have that. So What is that? What is the correlation between that? This is a constant. So the correlation between a random variable and the constant is equals to what? It's 0. If we have an ideal model, the correlation is 0. If the correlation is 0, what is the covariance? Of course, it's 0. So you can see, if we have a right-fitted model, if our model exactly estimates the true function, this one is 0. We don't have any optimism. We don't have any bias. The model is perfect. So we can just use the training error. You see that? But what is the overfitted model? Overfitted model always not estimating f, but estimating the y. So in that case, you can see the yi hat now becomes the yi. I'm talking about the extreme case, okay? So one extreme is the ideal model, perfect model. And the other extreme is extremely overfitted model. Then the yi hat becomes what? Becomes yi. We estimated all the points perfectly. So that's a overfitted model, right? So yi hat becomes yi. Then what is the correlation between two random variables which are the same? The correlation is what? The correlation is 1. Is that right? The correlation is 1. So what is the covariance? The covariance is maximized. That's the square root of the variance of yi times variance of yi. So that's the largest you can get. So you can see when we overfit it, this one will be very large. So we have a large optimism. That's no good. So overfitting gives very low. So that means for the overfitted model, we should not use training error to estimate, because the true in-sample error is much bigger than the training error. You see that? Okay, I won't talk about the technical details, how to prove that and why this. So this just, I'm using some extreme example to help you to appreciate or maybe understand what is the meaning of that. Okay, so ideal case should be the covariance is 0. That model is the true model. But overfitted case, this one will be very large. Okay, after class, you think about what about the underfitted case. Yeah. Okay, so we can also show that if the model is additive and the model is a linear fit model, and we can show that the expected value for the optimism is this one. So what is D? D is the number of variables, and the N is the sample size. Sigma epsilon square, that's the building errors. That is the variance for the random errors. Okay, and we can show this. So based on that, people says, okay, that's easy. Now we can get this one. We can prove this is expected value of the in-sample optimism is this one. So then, in order to find the one that minimizes this one, how about that? How about we move that part to the left-hand side? Okay, so we have the expected in-sample optimism, right? Plus the training error. Because when we move it to the left-hand side, the negative sign should becomes to positive sign. Is that right? So instead of using the optimism, we have the expected. Why? Because we now have these results. So that gives us the training error plus this term. And that can be used as an estimate to estimate the in-sample error. Okay, and that is the in-sample error approach with adjustment. Okay, and that is called malloc-p. I believe most of you should heard this name, malloc statistic. What is malloc statistic? It is the training error plus 2 times d divided by n times that. And that is what? Where does that term come from? It is the expected value of in-sample optimism. Okay, and why we need to plus a test training error? Because we move that part to the left-hand side. That becomes the estimate for the in-sample error. Okay, so that is the underlying story that why we have this malloc statistic, because this is used to estimate the in-sample error. Okay, and similarly, those AIC, BIC, the Archiiki information criteria is a more general setting because the malloc only applies for the squared errors. What if it's not squared errors? So we need some more general cases. Later we will talk about generalized linear models. We use the log likelihood instead. So this is more general. Okay, so AIC is changing the training error to the log likelihood. So you can see it's very similar to the malloc statistics. Compared to the malloc study, it's very similar. In fact, we can show that if the log likelihood here belongs to a Gaussian model, in other words, the random error follows a normal distribution, then the AIC and the malloc are equivalent. Okay, so that's the equivalence between AIC and the malloc for the Gaussian model. Gaussian model means that the random error term follows a normal distribution. Okay. And another one is Bayesian information criteria. It's a -2 log likelihood plus that. Okay, so you can see AIC, BIC, DS, they are very, very similar, right? These ends is just it doesn't matter. We can remove these ends. Why? Because AIC's value, we choose its own value has no use. The AIC, BIC is useful when we compare the model. No one will say, okay, this particular AIC value has its meaning. No, AIC is used to do the model comparisons. Okay, so if we multiply it by n, it doesn't matter. As long as you apply to all the models, okay, it's the same. So we always choose for those information criteria, the smaller the better, right? Okay, so you can see they are almost the same. So the only difference is what? Is for the AIC, we have 2 times D. For the BIC, it's log n times D. The rest part are the same. So that tells us, so this is the penalty part, penalty on the model complexity. So the D is the dimension or the number of variables in the model. So this one is 2 times D. This one is log n. Which one is larger, 2 or log n? Most of time, log n is larger, right? So this one is usually larger than 2. So this one is larger. So this one means the BIC put more penalty on the model complexity. Why I say penalty? This also has the similar idea like lasso. The first part measures how good the model is. If a model fits the data very well, the first part will be large or small? Small. Why it's small? For the log likelihood, it should be large. That means the model fits the data very well. But if you multiply it by -2, then the smaller the -2 log likelihood, the better the model fits. You see the difference? Okay, so this one measures how good the model is. The smaller, the better. But this one measures the complexity of the model. So you can see the more complicated the model is, the better the fitting. So if we have a complicated model, this term will be large. We have a penalty on the model complex, but this term will be small. We have a very good fitting. Okay, if we have a simple model, we reversed. This will be large. We have a bad fitting. We have fitted the data poorly. But we have a small panel because the model is simple. We have fewer variables. So it's a trade-off. So the optimal model, which makes the AIC or BIC or other information criteria smaller, is as a trade-off between the goodness of fitting and the penalty on the model complexity. And that's the underlying idea for the information criteria. And they are all these criteria belongs to the first one, in-sample error approach. So these are with adjustment, okay? So these approach, we don't need to split the data into training and test. We just use all the sample to fit the model. But when we evaluate, we add some penalty. Okay, so that's the in-sample error approach. We find the model not to minimize the generalization error, but to minimize what? In-sample error. Is that clear? So that's not our ultimate goal, but that's good. So, and also the fitting process is very simple. There's no randomness. We don't need to like randomly do like a cross-validation. For the cross-validation, there's randomness here. So here, there's no randomness. So it's simple, fast, and it particularly works well for the small data set. Okay, so that's the in-sample approach. Now let's see the internal approach. Now, before we see the internal approach, let's see some example for the AIC, BICs. So here, this is a speech recognition example. So this is the phoneme data set. We have two phonemes, R in the vowel in the dark and the R vowel in the water. Okay, so we have a training set, we have a test set with the figure shows 15 periodograms on 15 samples for each class. So we have 30 samples. 15 are R, 15s are R. Okay, and we use these periodograms to do the classifications. So here, the orange curve shows the training error, and the blue curve shows the test errors. Okay, and the green curve shows the AIC values. So you can see the training and the horizontal axis shows the number of bases in the model. So the larger number of bases, the more complicated the model is, right? So left-hand side models, so the models on the left-hand side are simple models. The model on the right-hand side are complicated models. So you can see the training error, orange curve, monotonically decreasing when the model complexity increases. But the test error, which is the blue curve, is a U-shaped curve. And the AIC curve, which is the green curve, have the similar shape as the test error. So that gives us some confidence that we can use the AIC as a proxy for the test error performance. Okay, so we can use the AIC to select an optimal model. Okay, so this is using the log likelihood, and this using another loss function. That's the 0-1 loss. Remember, for the classification, we have two loss function, 0-1 loss, right? And we have the deviance. That's the -2 log likelihood. Okay, so that's these two. Okay, so the question is AIC or BIC, right? Because they are different. So which one we should use? They are from different perspectives. So AIC, a low AIC value means a model is closer to the truth. But AIC does not imply that the optimal model with the smallest AIC value is the true model. No, It just indicates the model is closest to the truth. The BIC is what? BIC is the model that has the highest probability to be the true model. Okay, and you may say, what's the difference? Still don't know the difference. So here, just give you some idea. AIC is more like a humble approach. So AIC approach does not assume the model space that we explored include the true model. So maybe the model space that we explored here doesn't include the true model. So true model is somewhere else. So here I use the AIC to pick the optimal model. That is the model in my model space that is closest to the truth, which may be not in the model space that we explore. And that's AIC. Okay, so BIC assumes the true model is in the model space that I explored. Then that optimal model selected by the BIC tends to have the largest chance to be the true model. And that's BIC's approach. And the way that I said closest to the true model or the highest chance, these are the asymptotic property. Okay, so what is asymptotic property? Not the practical sense. Asymptotic property means that when we increase the sample size larger and larger and converge to the infinite sample size, then the BIC will have the 100% chance to select the one that has the highest probability. And the AIC will have converge to the one that is closest to the truth. So that is called asymptotic property, not for a particular data set size. Okay, so you have to be careful. It's very technical. So there were thousands of papers discuss the AIC, BICs. Okay, so I'm just giving you some takeaway message, which is may help you to understand that, but without telling you the technical part. So which one we should use, you decide. But they have different properties. Okay, so if you think about the true model may be away from the model space that you explored, probably you should use AIC. Okay, if it's in the space, probably you should use BIC. But in practice, BIC always gives you the simpler model. Why? This is because the BIC has the heavy penalty on the model complexity. It's log m, it's greater than 2. Okay, so that's why BIC gives you the simpler model, AIC gives you the complicated model. Okay. Okay, now let's go to the internal approach. Internal approach, first the validation approach. Validation set approach is if you have a data set, you can split into 2 parts. One is the training part, the other is the validation part. Okay, so there's a question based on my teaching this course. Many students say, so what's the difference between training set, validation set, and a test set? Okay, so especially for the validation set and test set, what's the difference? So validation set, there's some subtle difference. Validation set is usually used to help us to select models. And the test set is the final evaluation of the finally selected model. Okay, so we use like a cross-validation or validation set approach here to help us to select the optimal model. After we select the final model, and we want to evaluate how good this model really is, and we can apply an independent test set. And that results is the final assessment of how good that model is. So If you skip the final approach or final step, then just you don't. So in practice, you don't have to split into three parts: training, validation, and test. You can just have training and validation. That's good. But sometimes we need a test set. Why? For example, let's say for your midterm project, which we will talk about later, you applied a field approach. You applied the artificial neural network. You applied the tree random forest. These are the three different machine learning approach. But for each approach, like for artificial neural network, you need to have the validation set to select some parameters. And for the random forest approach, you also need to use validation set to choose the optimal value for the parameter in the random forest algorithm. Okay, but after you choose the optimal artificial neural network model and random forest model, you want to final comparison for is random forest performs better than artificial neural network or not. So in that way, how do you do the comparison? So you need a test set to finally evaluate their performance. So that is the situation that you need training, validation, and test. Okay, so because many students raised these questions in the past, so I'm just explaining here. Here, the validation set you just split into training, and another set is validation. Fit the model on the training set, let's say the blue part, and evaluate on the orange part. Okay, so that's the validation approach. So let's see for the auto data set example, we can fit the polynomial models to use the horsepower to predict the MPGs for the for different car models. Okay, so here we use the validation set, and here we split the data into training and validation as a even split. 196 as training, 196 as validation. Okay, this is not a good splitting proportion. This is not, but this is just used for illustration. I will talk about what is the right proportion, maybe next time, okay? But here, just as an illustration, okay? So to see that here, this is one particular results, okay? That shows the MSE, mean squared error, on a particular split on the validation set, on a particular validation set. And this shows the 10 splits results. Because here, if you randomly split into training and tests and the validation evenly, you can have many different splits, right? This one just show you one of them, but this one shows 10 of them. You can see the problem for the validation approach is what? It's highly variable, right? And this one, the horizontal axis shows the degree of the polynomials regression. Okay, so each curve represents a particular split. So different curve, like for the curve at the bottom, which degree is the optimal? It should be what? It should be this one, right? Should be the degree is 7, because that's the one that gives the minimum. Okay, but let's see, what about the second lowest? Probably it's this one. The degree 2 is the best, because that's probably the lowest. So you can see it gives us lots of random variations. That's no good. We need more stable evaluation results, right? So that's the problem for using the validation approach. So cross-validation is probably the better approach, okay? So let's look at the k-fold cross-validation first. So what is k-fold? K-fold means we split the data into K part. K is just like a KNN, is the number of fold. Okay, let's say we have a 5-fold. Okay, so K is 5. So we evenly split data into five-fold, five part. And you may ask, what if we cannot have an even split? Close to it, okay? If you cannot exactly the same size, just approximate. Approximately the same size. Then use one of the fold as a validation. The rest combine together as a training set. Fit the model, predict on the validation set. And we get the validation error, or we get the error from this validation set. Let's say this is a regression. We use MSE, let's say. So we have an MSE for the fold is 5. Then we use the other 4 folders as the training set, but the 4th one as a validation set. And then we fit the model and predict on the 4th folder. So we get MSE for the 4th folder, MSE4, and so on. Then we have the 3rd, 2nd, and 1st as a validation set. And then after that, we add all these 5 MSEs together and take the average. That will be the overall performance. And we have a name called cross-validation error. It's not just validation, it's a cross-validation, because each observation has been appeared once and only once in the validation set. So that's called cross-validation, K-fold cross-validation. Okay, and if each fold contains only one observation, then that's called the leave one out cross-validation. That means each fold, we just have one single observation. Then we just do the cross-validation with n folders, right? Okay, so we are running out of time, so let's stop here. Next time we will talk about, continue to talk about the model assessment, and hopefully we can finish that in the first half, and then the next half we will start to talk about the nonlinear smoothing. Okay, and don't forget to work on the homework 3. Okay, and if you haven't turned in the homework 2, turn in the homework 2 as soon as possible. Any questions? Okay, let's stop here.